I think it's important to get a concept of how the derivative of a function fits in with the actual function itself. So I'm going to graph both. I'm going to graph a function and then graph its derivative, and you can see some quite interesting things about it. Let's have a look here. We've got y equals 12 minus 4x minus x squared. And say you wanted to do a quick sketch of that, where you can see that when x equals 0, y equals 12, so it's going to cut at 12. So let's just draw up some axes here. So let's say that's the point 12. So we're going to go through there. And if I want to find out where it cuts the x-axis, I should, so x-intercept is when y equals 0. So we got 0 equals 12 minus 4x minus x squared equals, I'm going to factorise that, we've got 6 and 2. So we've got 6 plus x times 2 minus x, I think, plus 2x minus, yes. So what makes that equal to 0? X equals 6, x equals negative 6, sorry, we'll make that first one 0. What makes this equal to 0? Or x equals 2. So it's going to cut at 2, negative 2, negative 4, negative 6. So it's going to cut at those 2 points. And it goes through there. Now, because it's x squared, it's a quadratic, so it's going to be in the shape of a parabola. And because we've got this negative here in front of x squared, means it's going to be an upside down parabola. So if that is positive, you get a smiley parabola. If it is negative, you get an upside down smile, which is a frown. So we get that. So it's going to go something like that. So that's our graph of y equals 12 minus 4x minus x squared. If we do dy dx, we find the derivative of that. And the derivative of a constant is 0, so the derivative of minus 4x is just minus 4, and the derivative of minus x squared is minus 2x. So that's the derivative of our original function. This tells me the gradient at every point on this graph. It can be calculated by negative 4 minus 2 times whatever the x value is. As you know, the gradient at every point, or strictly speaking, the gradient of the tangent drawn at every point, is going to change. The gradient of a point here is going to be quite different to the gradient of that tangent. This one's going to be positive, that one's going to be negative, and so on. So depending on the value of x as to what the gradient will be. So it might be a really nice idea if we actually do this on another graph straight underneath. So if I draw this, now instead of, this was y and this is x, so this will still be my x. Well, let's move it up a bit here. So that's still my x, but instead of it being y, this is going to be dy dx, or the gradient. You can see that it's going to cut at negative 4. And we can calculate where it cuts the x-axis. The x-intercept is when dy dx equals 0. So that's for this graph here. So we've got 0 equals negative 4 minus 2x. So we've got, take that over, and we get 4 equals negative 2x. Divide by negative 2, we get x equals 4 over negative 2, which is equal to negative 2. So it's going to cut at negative 2. So if we do it straight underneath, there's my graph, straight line. It's a linear function. So this is my graph of dy dx. Okay, so how do these all line up? Okay, if we've just look at our function up above, you can see that the gradient of the tangents is starting to slow down. It's quite steep, not as steep, getting less steep, until it gets up to the very top here. And a tangent drawn at the top will touch the graph at one point. And that corresponds to that point there. At x equals -2, we have 0 gradient. This is the gradient, dy dx down here. And here is 0, so it's going to have 0 gradient. The gradients at all these red ones here is positive, and that corresponds to all these up here, from there to there. All those x values is going to have positive gradient. Forget about the fact that this is sloping down. We'll talk about that in a minute. So at x equals -2, we have 0 gradient, and then after that, let's do them in blue, all these tangents are going to have negative gradients. And that corresponds to all of these down here are going to have negative gradients. So that's where the gradients is negative. Anywhere across there you get negative values for dy dx as you go across. So this, which is the dy dx, and happens to be for all quadratics, dy dx is going to be a linear. And you can see that this is an important point when dy dx is equal to 0. In other words, the tangent drawn at that point is going to be parallel to the x-axis. And we can use that in later things to find out what's the greatest value of a function, and I'll go through an example in a future video on that. But for the time being, just understand what the derivative tells us. It tells us the instantaneous rate of change, or the value of the gradient at any point drawn to the curve. And this allows you to interpret what happens on either side of x equals -2, or the turning point in this case.